Welcome learners. In previous video we have seen how to implement RL and RC circuits and how to observe transient analysis. So today we will see uh, for RLC circuit. So for that I am opening the PSpice software. So this PSpice software already I have saved the file. So now I am opening the same file. Circuit that we have designed in the last session. So where I have taken RC circuit and we have designed for RL circuit for single value of resistance. RL is equal to 1, RL is equal to 5, and then R, so L is equal to 10 ohms. So now the input remains same if you observe the input. So at T1 is equal to uh, 0 seconds, and what T2 is equal to 1 nanosecond, like that. So we have even up to 3 milliseconds. So the input has remained constant. Now based upon the values of R, L, C, we have kept L and C as constant and we have changed the value of resistance. Now we'll observe what is the current that is flowing through the circuit, how it behaves. So if you observe here, now I am run this simulation. So here comes the output file. In the output file, so I need to observe the current responses. For first one, I of R1, I of R2, I of R3. So these are the current waveforms that we have obtained for different values of resistances. So this is for R1 resistor, and this is for R2 resistor, and similarly this is for R3 resistor. Similarly, we can observe the voltages also. For that I am showing the voltages. So voltage across L1, L2, L3. So V1 of L1, L2, L3. So these are the voltages across the inductor for different values of resistances. And this is for second resistance R2, and for third resistance this is R3. So these are the values of voltages across inductor. Similarly, we'll see the voltages across the capacitances. So V of C1, C2, and then C3. So these are the voltages across C1. So this is for second capacitance, and this is for third capacitance. Okay. So these are the current, voltage, and voltage across inductor and voltage across capacitor in an RLC circuit when it is excited by a step input. So now we'll see uh, for a sinusoidal excitation. For that we need to change the circuit. For we'll see for R, RL, RC, and RLC circuits. For that I am taking a new file, new project. So this is AC transient. So click on OK and then click on blank project. So this is the blank window I got. Now, so here first I need to take a sinusoidal waveform. So here in sources, I need to go for sources. Under sources, I need to search for not VAC, I need to go for sine, V sine. So sinusoidal voltage, I need to place the sinusoidal voltage and I'll take RL. So RL load. So for that, so I need to go to analog and R. So I have placed the element R. Similarly, L. Similarly, I have placed the L. Now I need to connect all the elements. For that, I'll take the connection and then similarly here. So from R1 to L1. Similarly from L1 to V1. So then I need to connect the ground terminal. So I have connected the ground terminal. Next, I need to give the values for resistances and the input voltage. So for the first, we'll give 0 volts and then amplitude, I'll take it as 100 and frequency, I can take it as 50 hertz. Now this is for L1, so I'll take 10 ohms. And so let us consider R is equal to 1 ohm, L is equal to 10 millihenry, and the amplitude of your sinusoidal waveform is 100 volts, and the frequency of the sinusoidal wave which we have considered is 50 hertz. Let us now simulate this so 50 hertz frequency means up to 40 milliseconds. So and click on OK and then run the program. So after simulation, so check the outputs. So we need to check the outputs across. First, we'll take the input voltage V of V1. So input voltage you are getting it as 0. So at 20 milliseconds, so one cycle is completed. Now we'll observe the voltage across L1. How the inductor voltage. So inductor voltage, if we observe here from 20 millisecond, so it is ahead the value of voltage, so voltage waveform. Similarly, we'll consider the current waveform also, or current flowing through the circuit. So this is the current flowing through the circuit. So I'll increase the width of this waveform. So that is the input voltage waveform. This is the current waveform, current flowing through the circuit, and this is the this is the current waveform. The red one indicates the voltage across the inductance. So this is your current waveform. Now always if we observe here, if I take 20 milliseconds is at the starting point, so where here it is the starting of the simulation. Now for better understanding, I'll start considering at 20 millisecond. So at this point the supply voltage is at 0 degrees and it forms a sinusoidal waveform. After that, if we observe the current reaches 0 at uh, less than 90 degrees. Why? Because we have taken an RL circuit. If you consider pure inductance, it always starts at 180 degrees, and the voltage with respect to the inductance we have seen here. So this is how we need to simulate RL circuit with a sinusoidal input. Similarly, we can do it for three different values of resistances. So let us say for R is equal to 1, and then for R is equal to 10, and then for R is equal to 50. So first I need to connect this circuit from 2 to the reference. Similarly here, now I need to change the value of names of the sources V1, V2, R1, R2, L1 to L2. Similarly, for the third circuit, R3. Similarly, for the circuit, L3, and the voltage V3. So after doing this, now I'll simulate the circuit and we'll observe the waveforms across the resistances of each circuit. So this is 10, sorry, this is 5. We'll take resistance as 5 ohms and this is as 10 ohms. Inductor values remain same. Again, I'll simulate the circuit and then I'll check the current waveforms I of R1, R2 and then R3. So if you observe here, these are the different currents that are flowing through the circuit with, in case of R1, R2 and then third resistance R3. Okay, R1, R2 and then R3. If you want, you can simulate it for less than 1 ohm also, 0.1 like that. If you clearly observe the difference between the currents. So what happens when resistance increases, the magnitude of your current waveform decreases. Similarly, we'll check the voltages across the inductors. So with respect to the supply voltage, so V of L1, L2, L3 and V of V1. So these are the waveforms that are related to your voltages across each inductance when it is subjected to a sinusoidal input. Similarly, we'll do it for RC circuit. So for that, I'll take one more resistor, one more file, new project file. So here, sine RC. So create blank project and then take the elements that are needed. So from first I need a resistance, capacitance. So one capacitor and one inductor, sorry, not one resistor, and then a sinusoidal input voltage. So for that I need to go for sources and then sinusoidal input, and this is it. Now we need to connect these elements. So we need to place the ground and then the value of voltage source, offset value will take it as 0 and then amplitude as 100 volts and then frequency 50 hertz, resistance value 1 ohm and then capacitance value 50 microfarad. 50 microfarad. Now we'll simulate this circuit and we'll observe the current voltage and voltages across capacitor in a RC circuit. So here I'm creating a new simulation profile. So here again you need to take it for 40 milliseconds for 2 complete cycles and then simulate this. So once simulation is completed, we'll get this window. So first I need to find the current flowing through the circuit. So if we observe the current, so it is at 0, it starts at maximum and then it reaches. So when it is compared to the voltage source, V of V1, so the magnitude is very less. Uh, so we'll see the current voltage across the capacitance VC1 and then V1. So it is almost all following the supply voltage. But if you clearly observe that the voltage always lags. So if you zoom out it here, or I can zoom out it here, so it is always lagging the reference voltage or the input voltage. Similarly, this I can do it for three different types of resistances. So for different values of resistances. So connecting the capacitor to the ground, and then here also capacitors to the ground, and then changing the value names of the elements. So R2, and then C2, and then V2. Similarly here R3, C3, and then V3. Okay, and then value of resistance is also, previously it is 1, now I'll take it as 10, and here it is 15. Any values you can take. Now you need to observe the current magnitudes and voltage across the each individual capacitor. So for that I'll run the program once again. So then I'll get this window from where first I'll observe the current waveforms, what happens to the magnitude of the currents. So if you observe here, with different values of resistances, the currents are like this. Similarly, if you observe the voltages with respect to the supply voltage, so V of C1, C2, C3, V of C1, C2, C3 with respect to V of V1. So these are the voltages. As the capacitance or resistance values decreases, the uh, difference between the reference quantity and the capacitor voltage increases. So this is how you need to observe the transients in an RC circuit when it is excited with a sinusoidal input. Now we can take this for an RLC circuit with the same elements, but extra I need to add one inductance, that I'll add it here in the same circuit. So first I am deleting the wires and I need to add inductance. So for that I need to go for analog, and then I need to search for inductance, and then I need to connect the inductor. So L1, L2, and then L3. Three inductances I have taken. Now I need to connect these inductances with the capacitance. Here also is the same, and I'll keep the inductance value the same as that of here, the given value 10 microhenries, and then we'll observe what is the difference that you get in the currents and voltages. So here we got, first we'll see the currents across R1, R2, R3. So if you observe here, these are the currents in an RLC circuit. If you want to change, you can change the value of resistance, inductance and capacitance, and you can easily observe the variations in the voltages and current. Similarly, we'll observe the voltages across L1 and C1. So first we'll observe the voltages across L1. So how the voltage across inductor varies. So V of L1, L2, L3. So this is the voltage across inductance. Similarly, voltage across capacitance V of C1, C2 and then C3. V of C1, C2 and then C3. So this is the voltage across V of C1, C2 and then C3. So this is how you need to apply a transient analysis in an RL circuit, RL, RC and RLC circuit for a step input and a sinusoidal excitation. And you can observe for different values of resistances how the current, voltage and voltage across each element varies. Similarly, we can include a switch to observe the transient analysis in an RLC circuit, and the same can be applicable for RC, RL and RC circuits also. Let us see how to attach a switch to this circuit such that we are switching on the circuit at t is equal to 20 milliseconds, and after that what happens to the current and voltages across the elements in the circuit. For the switch we need to go for so here we need to go for analog miscellaneous. In that, if you scroll down, you will come across switch close, SWT close. So click on OK on that, and then place the switch before the elements, in between the source and the elements. So here I am placing the switch in the three circuits. Now I need to connect this switch to the circuit. So let us connect this. So from V1 I am connecting it to switch, and then here also V2 to switch, and then switch to R2. Here also the same thing, V3 to switch and then switch to here. Then after this, so if you observe here, at t is equal to 0, the switch is closing. So if you observe on the top, we have t is equal to 0 here, which means the switch is closing whenever the simulation starts at t is equal to 0. The starting time of the simulation, it is nothing but the switch is closed. So this can be modified as double click. So if you change this, if you slide this one at this t close, so at the here I am giving it as 2 milliseconds. At 2 milliseconds this switch will be closed, and then here also for the second circuit also the t is equal to 2 milliseconds. I am closing the switch after the um, simulation has been started, and after 2 milliseconds after the simulation started, I am switching or closing the switch. So and we'll observe the current transients in the current transients and voltage transients. 2 milliseconds uh, now. So after changing this, so if you observe on the top, we have observed 2 milliseconds. Now the switch closes at 2 milliseconds. So 1, 2 represents the two terminals of your switch, whereas on the top 2 milliseconds shows at what time the switch will close. Now if you run this simulation, we'll observe what is the difference for the previous simulation and this simulation. Now, so here I am interested in seeing the currents that are flowing through the circuit. Now, if you clearly observe here, before the time t is equal to 2 milliseconds, the current circuit is 0. Why? Because the switch is in open condition. At t is equal to 2 milliseconds, suddenly we are turning on the switch. Because of this sudden change in the voltage across the elements, so the transients occurs. So if you observe here, I am zooming this part of the waveform. So these are the current waveforms at t is equal to 2 milliseconds. When I suddenly close the switch, so the current magnitude changes abruptly like this. Similarly, we can see the uh, magnitudes of the other elements. So first we'll see, so this is the voltage across R1, and this is the voltage across, sorry, current across R2, and then this is the current through R3. Okay, now we'll see, similarly we'll see the voltages across L1, L2, L3. So voltages across L1, L2, L3. So if you observe here, before time t is equal to 2 milliseconds, so there is no supply is connected. At t is equal to 2 milliseconds, suddenly the supply is connected. Inductor acts as open circuit, so therefore the voltage will abruptly increase, which is nothing but your supply voltage, and then it gradually decreases. So these are the current, sorry, voltage across L1, inductor L1, similarly L2, and then L3, voltage across L3. So voltage across L3, and similarly we can see the voltage across the capacitances. So V of C1, V of C1, C2, and then C3. So voltage is across the elements capacitor C1, C2, and then C3. When compare, you can also compare it with the source. So V of V1. So this is how you need to analyze the transient analysis in and series RL, RC, RLC circuit.